Greetings and welcome to All Things Physics, where we attempt to illuminate the hidden world using the lens, or mirror, of science. Today I want to discuss something that's truly remarkable. It's a technique that allows us to visualize things that are normally invisible. Check it out. What you're witnessing here is a large beaker that's been filled with carbon dioxide being poured into a smaller beaker. Of course, we can't see air or carbon dioxide, so it doesn't look like there's anything happening at all. What's not obvious is that this experiment is being performed inside a Schlieren imaging system, which allows us to see things that are not normally visible. Let's watch the experiment again, but this time when viewed through the Schlieren system. Notice that you can now see the flow of carbon dioxide as it's being poured from one beaker into the other. Clearly, there's a lot going on here that's usually hidden from view. Hopefully, it's obvious that such an imaging system is a useful tool for researchers who study fluids. But how exactly does it work? I mean, what kind of optics are necessary to accomplish this seemingly magical feat? In this video, I'll explain exactly how this experiment was constructed and provide a detailed overview of the physics behind a Schlieren imaging system. The word Schlieren is German for streaks or smears, and is used to describe the types of images that are typically observed in these systems. This technique was first described in Robert Hooke's book Micrographia, which was published in 1665. Today, Schlieren imaging techniques have been used to study engine plumes from the space shuttle and shock waves from supersonic aircraft. There are many different types of Schlieren systems, but they all rely on the same basic physics. The type I'll be discussing is one of the simplest, and at the heart of this system is a concave spherical mirror. However, for completeness, I'd like to begin by discussing the behavior of a regular flat mirror. If you already have a solid understanding of flat mirrors, you might want to skip over this portion of the video. For much of this video, I'll be using a very impressive ray optics simulator that's freely available online. It's easy to use and fun to play around with, so I'll leave a link to the program in the video description. Here, I've set up a flat mirror surrounded by an absorbing wall, and I want to consider a single light ray, which you can think of as a tiny laser beam. In this simulation, I can control both the direction the light travels and the position of the light source. Now, the way a mirror works is exactly as you might expect. Any light ray will reflect off the mirror at an angle that's exactly the same as the initial angle. This is known as the law of reflection, and in the language of physics we say that the angle of reflection is equal to the angle of incidence, these angles being measured with respect to a line normal or perpendicular to the surface. To understand how the mirror creates an image, we need to recognize that each point on an object, such as a book or a person, scatters ambient light in all directions. To keep things from getting too messy, we'll consider only light rays that scatter in the direction of the mirror. Although we could make things more realistic by using a continuum of light, it's more instructive to be able to see the individual light rays. Normally, ambient light scattered by an object travels directly to our eyes. Here, however, the light rays reflect off the mirror and appear to be coming from a point located behind the mirror. We refer to this image point as a virtual image because the light rays don't actually emanate from this point. Using the law of reflection, it's not difficult to show that the image resides the same distance behind the mirror as the object is in front of the mirror. As we move the object around, the image point moves in response. But notice that the image point always remains sharply in focus, a unique feature of flat mirrors. Although we have only considered a single point, this same thing happens for every point on the front side of the mirror. In other words, every point in front of the mirror will have an image point located an equal distance behind the mirror, And this is true even for points that are not directly in front of the mirror. Of course, to see such images requires that you be positioned in the path of the reflected light rays. The fact that every point on the front side of the mirror has an image point located behind the mirror leads to a remarkable conclusion that an entire world can be reflected in a mirror, regardless of its size. In this sense, a mirror can be thought of as a window into a perfectly reflected virtual world. To understand the Schlieren system I'll be discussing, we need to transform the flat mirror into a curved mirror. If the object is close to the mirror, the behavior is very similar to a flat mirror, although the image now appears farther behind the mirror. One major difference from a flat mirror is that the light rays no longer converge perfectly at the image point. Such spherical aberrations make the image somewhat blurry and imperfect, and this effect is exaggerated when the object is moved off the central axis of the mirror. As the object is moved away from the mirror, an interesting thing happens. Specifically, once the object is beyond the focal length, the location of the image appears on the same side of the mirror as the object. In this case, the light rays actually converge and emanate from the image point, so we call this a real image. Of course, the light rays don't converge perfectly due to spherical aberrations, particularly when off the central axis. In fact, for a spherical mirror, there's only a single point where the light rays converge perfectly at the image point, and this is when the object is placed at the exact center of the sphere. At this location, all of the light rays are locally perpendicular to the mirror's surface, so they reflect directly back to the center of the mirror. If we now move the object slightly away from the center point, the convergence of the light rays remains nearly perfect. However, now the object and image points are physically separated in space. It is this geometry that lies at the heart of our Schlieren imaging system. To create the Schlieren system, we use a point light source as the object and then introduce a small item to block the reflected light at the image location. In practice, we use a metal wire as the light block. Believe it or not, that's all there is to it. We just need to add a camera and we have a Schlieren imaging system. To understand how the system works, imagine placing a camera directly behind the light block. Normally, none of the light from the source will make it into the camera, since it's all blocked by the wire. Thus, the key feature that makes a Schlieren system work is for some of the light to deflect past the wire so that it's seen by the camera. To understand how this can happen, we need to take a short detour. It's well known that light rays are deflected when passing from one material into another at an angle. Here's an example when light travels from air into plexiglass, but the same thing happens when light travels from air into carbon dioxide or some other gas. This phenomenon is known as refraction and occurs because air and plexiglass have different optical properties. In this case, the property of interest is called the index of refraction, and the amount of bending is governed by Snell's law. Refraction can give rise to all kinds of interesting effects, and allows us to create such things as lenses, which are used in many different devices, including microscopes and telescopes. Unfortunately, exploring such instruments would take us too far afield from our present goal. So for now, we just need to know that light rays get deflected whenever the index of refraction changes. For a gas, the index of refraction depends on its density, which in turn depends on pressure and temperature. This means that light will also be deflected when traveling from cold air into hot air, or vice versa. You may have observed this phenomenon as a shimmering effect when light travels over a hot surface, such as a road or runway, or, as demonstrated here, using a hot plate. For our purposes, what's important is that when light travels through a patch of hot or cold air, it gets deflected by a tiny amount. But this deflection is enough to bypass the light block in the Schlieren system and make it into the camera. To demonstrate this effect, I've outlined a small blob of air in front of the mirror in which I can control the index of refraction. If I decrease the index of refraction by a tiny amount to simulate a blob of hot air, then we see that some of the light gets deflected past the light block and into the camera. Similarly, I can simulate a blob of cold air by increasing the index of refraction, and again, we see that some of the light gets deflected past the light block. In this way, a Schlieren optical system can be used to visualize small density changes in the air that would normally remain invisible. If you're watching carefully, you may have noticed that there's a small difference in how the light rays get deflected depending on whether the blob of air is hot or cold. We'll return to this observation shortly. In the meantime, now that we have a basic understanding of how a Schlieren system works, let's take a look at a real system. Our system utilizes a 16-inch diameter spherical mirror with a radius of curvature of 4 meters. The large diameter provides a sizable viewing area, while the curvature results in a very sensitive system. 4 meters away is the light source and light block. The light source consists of a bright LED that passes through a diffuser and then through a small pinhole with a diameter of about 0.5 millimeter. In fact, using an adjustable slit instead of a pinhole delivers significantly more light, and this leads to much better results overall. After reflecting off the mirror, we carefully focus the image of the slit onto the wire light block that sits in front of the camera. As a technical aside, it's worth mentioning that any light deflected along the direction of the wire will not make it into the camera. Thus, our Schlieren system is not sensitive to density variations along the direction of the wire, whereas it is maximally sensitive to density variations perpendicular to the wire. Once everything is carefully aligned, the system is ready for action. So here's what the Schlieren system looks like when it's physically set up. We have our light source right here, and it shines down to this spherical mirror. We have an object in front. And then all that light comes back and hits this wire block and then goes into the camera. And if everything is working according to plan, we should actually see a Schlieren image right there, and there it is. Maximum sensitivity is achieved when there's a small amount of light leaking past the wire, which leads to a gray background in the mirror. Here you can see some rather impressive air currents that result as the temperature of the air changes in response to my hand. It's worth noting that the density changes here are incredibly small. A more dramatic example is seen when the air responds to an ice pack. In this situation, the air is cooled, becoming denser and falling toward the ground in a spectacular manner. Believe it or not, the air behaves this way all the time. We're just unaware of it because it's normally invisible to us. At the expense of some sensitivity, we can narrow the slit to create a pure black background, which provides a nice contrast. Watching the air rising above the candle flame like this is rather mesmerizing, but it does make me wonder what exactly we are looking at. It might seem reasonable to think that the bright and dark areas in a Schlieren image correspond to the density of the gas, but it turns out to be somewhat more complicated than this. Interestingly, we can get a clue about what we're seeing by adding colored filters to our light block. Here, we've attached red and green filters to the sides of the wire, and this will provide us with additional information. Now, in addition to seeing a colorful image, we will also be able to tell which way the light is being deflected. Let's see what happens. In this experiment, we have an ice pack on the left, a cup of hot water on the right, and the wire is oriented horizontally, which prevents us from seeing horizontal density variations. As you can see, the colors surrounding the hot and cold objects are reversed. Had the wire been oriented vertically, we would then see colors on the sides of the objects instead of on the top and bottom. We can understand this behavior if we return to our ray diagram. As we have seen, there's a subtle difference between how the light rays are deflected depending on whether the blob of air is hot or cold. I'd like to now take a closer look at what's going on here, but to try to make things as clear as possible, I'm going to reduce the number of light rays, move the camera away from the light block slightly, and increase and decrease the index of refraction by a slightly larger amount than before. When the blob of air is hot and less dense than the surrounding air, it acts a bit like a diverging lens, which causes the light rays to focus behind the wire. Conversely, when the blob of air is cold and denser than the surrounding air, it acts a bit like a converging lens, which causes the light rays to cross paths as they focus in front of the wire. Notice that in both situations, it's only the light rays that pass through the edges of the blob that are deflected past the light block. Light rays passing through the middle of the blob remain blocked by the wire. As we'll discuss in a moment, this is a result of the Schlieren effect being dependent on density gradients across the field of view. For now, the important thing to notice is that light rays passing through opposite edges of the blob are deflected to opposite sides of the wire. Therefore, if we place red and green filters on the sides of the wire, then the blob of air will be seen as having red and green edges. But if we now switch to a blob of hot air, then the light rays no longer cross paths in front of the wire, so they now pass the wire on opposite sides compared to a cold blob. The end result is that the colors on the edges of hot and cold objects will be reversed, exactly as we have observed. Although the ray tracing diagram helps us understand why the colors on hot and cold objects are reversed, we still don't understand exactly what the colors represent. To answer this question, I had to dig through the literature on Schlieren imaging. It turns out that the angular deflection of a light ray traveling along the central axis of the mirror is proportional to both the density gradient perpendicular to this direction and the depth of the disturbance traversed by the light ray. The density gradient, which is another term for density change, is the critical factor here. Ultimately, this equation is a result of the speed of light being slower in materials with a higher index of refraction. But what this equation tells us is that positive density gradients will deflect light to one side of the wire, and negative density gradients will deflect light to the other side. In other words, the two colors represent positive and negative density gradients across the field of view. For example, consider the hot air stream above the candle flame shown here. As we move to the right, we find that the air density first decreases as we enter the stream, but then increases once we've passed through the center. Thus, the density gradient will be negative through the first half of the airstream and positive for the second half, which results in half of the hot air stream being red and the other half being green. To finish up this video, I'd like to show a few more examples of things we captured using our Schlieren system. In fact, the last one is somewhat puzzling, and I'm hoping someone out there might be able to help me figure out exactly what's going on. So if you want a challenge, be sure to stick around. Striking a match is always a highlight, and in this particular case, we captured some really beautiful images that show how the match smoke and Schlieren colors intermingle with each other. There's nothing particularly special about this scene, except that I wanted to remind you that everything you're seeing here is normally invisible. There's something almost dreamlike when viewing things through a Schlieren system. Here's a gas duster. and a blow dryer. Did you notice anything? The colors for the gas duster are reversed from the blow dryer, which tells us that the gas coming out of the sprayer is cold. This cooling is a result of a throttling process, otherwise known as the Joule-Thomson effect. This butane lighter shows a color pattern that's opposite from the candle we saw earlier. That's not because the flame is cold, it's simply because we happened to reverse the filters on the Schlieren system that day. What's interesting is that when the flame is blown out, you can still see the butane, and based on the color pattern, we can even deduce that the butane is denser than air. The last experiment I want to show is both interesting and puzzling. The setup needs a little explaining. So now that we got the Schlieren system up and running, we thought it would be kind of cool to see a smoke ring with no smoke. The way we're going to visualize it is to use carbon dioxide and then use the Schlieren system to see the difference in density of the gases. The carbon dioxide is being pumped into this cup. It's got a diaphragm here, a little balloon that we put on the end, and we've cut a hole in the front so that when we hit the diaphragm, it puffs out a little smoke ring, of course, with no smoke. So we're going to try and visualize carbon dioxide rings using the Schlieren system. We'll see if it works. If you've never seen smoke rings produced from a cup like this, here's what they look like when the cup is filled with fog made from dry ice and water and filmed in slow motion. And here's our attempt to view them using our Schlieren system. Okay, you ready?
Yep. Try a little stronger. Yep, that's nice. Try again. That was pretty fast, but yeah. That was really good. That was also good.
I have to admit that I was pretty jazzed when I first saw these images. I wasn't sure the experiment would work, but to see these exquisite ethereal rings floating through the air was immensely satisfying. And notice that we're actually seeing two rings, even though the cup only produces a single ring at a time. In other words, not only are we seeing an invisible carbon dioxide ring, but we're also seeing its reflection. Isn't that incredible? Normally, the reflection in our Schlieren system is not very noticeable because the object is placed close to the mirror. But in this case, the reflection is quite clear, and it made me realize that it wasn't obvious, at least to me, which rays are responsible for the original ring and which are responsible for the reflection. I mean, how exactly do these images arise? I think I've come up with a satisfactory explanation, but if anyone out there has some insight on this issue, I'd love to hear your thoughts. So please leave a comment below or contact me directly. And finally, if you enjoyed this video and would like to see more content like this, then I hope you'll subscribe and share the video with others who might appreciate it. And if you're truly inspired, you might also consider supporting this channel through Patreon. The link is in the video description. And with that, I'll bring this video to a close. I'm David Jackson, and this is All Things Physics.